So in the last video, we went over the coin game problem for midterm 2 of spring 2017. And here, so the idea is that we're given an array and each player can only pick the leftmost or rightmost value and they add that to their score. We want to find the best score for the current player. So in defining S of ij as the best score for the current player, so the max score for the current player can obtain with a subarray from I to j. And so player 1 is going to get two choices, right? Left or right. If player 1 takes the left, they're going to have the score of that value of that coin. And also the best score from picking a small array. And in this case, the smaller array is determined by player 2, right? So once player 1 picks the leftmost coin, player 2 now has that subarray and makes a choice of picking left or right. And player 2 is going to minimize the best score that player 1 can obtain with one of those choices, right? So here is a choice that player 2 picks left and right for both cases. And then we add the current value of the coin, and we maximize the bet's value, right? So it's a max of a min problem because we have two players that are adversarial, they're playing optimally and adversarially. So now we're going to implement this recurrence in various different ways. So the first way I'm going to show you is we're just going to go along and implement the most basic functions. So let's just implement this without any dynamic programming. It's just going to be recursive and no optimization whatsoever. So we have a couple cases. So let's do our base cases. If length 0, we can n is less than or equal to 2 to max of a, right? So this is just going to be these base cases here. And now we create our subproblems. So S1 is going to be the recursive call from a of I plus 2. Right. S2 is going to be the recursive call. Right. So let's define this. So S1 is going to be S of I plus 2 of j. S2 is S of I plus 1 j minus 1, right? So these two are the same, right? So we actually have the recursive tree is going to be 3 branches rather than 4 because these two share the same branch. And then S3 is going to be equal to, okay. So I know I did say that we're going to start off not optimal. So let me just make this. So you see how up to j minus, so this should be 2 onwards, 1 onwards, and minus 1. This is going to be the same thing. So if we were to just do not do any optimization, we have 4 cases. Minus 2. We have 4 cases, right? Because we have choose left is going to be, all right. So when I choose left, it's going to be the first value of the min of S1 and S2a. Choose right is going to be the last value plus the min of S2a and S3. And now we maximize our left and right. Right, so I did say that this is no optimizations. We have we have a branching factor of 4 at every recursive call. So there's going to be 4 to the n. without accounting for the fact that I'm also list slicing here, right? So that's going to be, each one of these is going to be, list slicing is going to be a deep copy, which means that each of these takes linear time, and we have branching factor 4, so our runtime is going to be 4 times, so runtime is going to be 4 of, sorry, so n of 4n. Yes. Okay, right? So note that, remember that this was what we talked about. You didn't need this, right? Because they're the same thing. So now, instead of having a 4 to the power of n, we're going to move to 3n. And no, let's not use that. Right, so this is still going to work, and our code here is going to run in n to the power of 3n. Right, so we have this. So the issue here, the first issue is that I'm doing a list slicing at every recursive tree. So let's change that in this one, where, so because I was doing list slicing earlier, and we can make that easier by not doing a list slicing, because I don't actually need to have a new array every single time, right? From our subproblem over here, all we need to know was that we had our 2 endpoints. So I'm going to define a new function. It's going to call coins. It's going to take in list of ij, and I'm just going to return 0 and length of -1. Might as well just make this here, right? So we talked about how we can reuse this, right? It's going to be the same logic, except now we're going to wrap it in a smaller function, in a helper function, right? So let's see, we got to change this, because this is going to be I is j, return 0. Oh, I mean return a of I. So here's the case where I can choose which one to use. I actually don't need. All right, that's okay. So here's the case where I can choose, make it actually similar to the base cases we wrote down earlier. Right. So we have the 3 base cases from here. And now let's implement this part. So our recursive call is going to be coins of I plus 2 and j. So this is saying that this subproblem is saying I pick left and opponent picks left. This subproblem I plus 1, j minus 1 is going to be either I pick left and opponent picks right, or I pick right and opponent picks left. And finally, we move to the case where it's going to be we both going to pick right. And now I make I and j, and we have our oh no, something failed. In object no attribute A. No, let's call A. Which line? Oh, my bad. Okay, cool. So that everything works. If you're not familiar with doc tests, so I'll just do verbose, right? Everything passes. And so what I did was that I went from list slicing to using indices like we denoted in our subproblem, right? So this is why these I and j is important, because I can directly make the recursive calls without reslicing my list, because I've defined the fact that ij means that I'm looking at a subarray of a to a and I and j, and nowhere in our recurrence relation do we actually use the other values of the subarray, right? So all I care about was a of I and a of j. So now I went from n times 2 to the power of n to runtime of 3 to the power of n only, right? Okay, but that's not good, right? Because what do you notice? Well, think about this. So let's come back to this array over here, right? So let's say I pick left, opponent picks right, and then we move on and we only give in like 8 and 4. How many problems do we actually, how many subproblems actually require the answer to this problem 8 and 4? A lot, right? Because I can pick left, opponent picks right, and then I pick left and opponent, let's see, let's make 9, right? So let's think about this case. I could pick left, opponent picks right, I pick right, opponent picks right, and we come down to 8 and 4. Or I can pick right, opponent picks right, I pick right, opponent picks left, we come down to 8 and 4, right? So there are a lot of different ways for us to go from our initial array, like in our recurrence, in our tree, right here. There are a lot of ways where we can reach this subproblem, specifically 8 and 4, which meant that at some point along these values, we start sharing subproblems, right? And that's the whole idea of dynamic programming, is that if we know that we can share these subproblems, I want to reuse it, right? So the first idea is that, okay, I define some subproblem in a recurrence relation, meaning that I have this subproblem that I can solve using smaller, using a result of a problem of a smaller input. In this case, our small input is going to be the subarray of A. And the second thing is that, okay, we know that when we traverse this tree, we see a point where they cross. So why do I want to recompute this tree down again if I have computed earlier? So the idea is, let's cache the value and only compute it once, right? And I'm just gonna use, here's my code. I'm gonna just, okay, so there's two ways of a cache that we can use here, but I'm just gonna make a dictionary cache. This basically caches ij to best score, right, for a subarray. J, okay. Now, let's take this back. Right, you see how I'm just copying and pasting the code because we're building off one another. Okay, first thing first is, okay, so let's think about which of these base cases do we not need. I said that we always need this case, right? So if we always need that case, let's keep it to the top. Okay. Now, one of these cases we are not needed, mainly because the base case of recursion is, the goal is meant to stop your recursion, right? So this will always stop recursion when we get down to one value. Usually, but by the way we define our subproblem, we take two values out at a time, which meant that this will only occur if we have an odd array. And then here are the two cases where we have an even array, right? If we reach 0, we have 2 elements left. I start off with an even array. So in this case, in the recursion part, one of these we can just take out, and it will work, right? Because, oh, yeah, this doesn't work because of the So this doesn't work because of this case, a 0. So if you want, okay, so let's keep this and take this out. But we don't actually need it. Right? The reason we have to keep this is because I could give you an empty array. You have to give 0 just for a edge case, but you could have kept the other one and put this out here, like if you have an empty array. But let's just keep this for more to keep it more generalized. Okay, here is where it gets interesting, right? You see how these are 3 subproblems we were talking about. So when I get to a part, I could think, okay, is this in my cache? If it is, we could just use it. Otherwise, not, right? So if I plus 2j in cache, I know S1 is going to be j. Now, if it's not, I do have to compute the value, right? I do have to compute this. I have to make a recursive call, but now let's keep the value. Let's store it. So the next time when I come to the same problem of I plus 2 and j at that specific I and j, I can just get it off from a cache. So same thing for S2. You know what? Let's just copy and paste. Okay, so S2 is going to be I plus 1, j minus 1. S2 plus 1, j minus 1, minus 1. Okay, so S2 and S3. Okay, it's gonna be I and minus 2. We like both players both players are gonna pick right consecutively. Let's make this S3. Okay, and now I make a choice here. Right, so this is my cache, and let's see this work. All right, so this is gonna work. Everything passes, we're good. So this might be a little bit too much, right? So this code is saying that, okay, before I make the recursive call, let's check everything in the cache and do it, and then like take it out if need be. A better way is a more cleaner way in terms of code. Could be we could do it like this. I'm just gonna copy the previous one because it'll make it easier. Well, it's okay. Okay, so we could do. Okay, so you see how instead of doing the cache check in here, we can do something better. Let's do it in the beginning. And note that this cache is shared as like among all recursive calls on coins, right? So ever since I moved from slicing the list to indices, I made the recursive call on the helper function. So you can use this cache and pass it as an argument, or you can use it up here, because in Python, any function you define inside a function can look at the variables of its parent function. Okay, so we can just do a quick check if I j in cache return cache if I j. Otherwise, okay. Otherwise we can do it out here. We have cache of I j is going to be equal to this. Oh no. Anyway, that's max of choose left and choose right. And we can just return. Okay. So now, so this is going to work as well, right? So rather than doing the check here, we take a recursive call and check at the very beginning before going through a body of a code. And if it's not a cache, return. Otherwise, we wait until the end and we cache the value and return the value. So I know that we are using a dictionary, which means that, like a hash table, which means that this might not always be constant time, as you have to traverse the bucket. If you really want to be, if you really want to go all out, you can just say, you can keep it a local variable, right? And this will make it better. Okay, cool. Now back up here, this actually can be, so I know that this like cache 2 is an improvement of this implementation, but if you don't want to do this, if you don't want to take the recursive call, there's a better way to do these check, is you do a not check. So if it's not in the cache, you set your value, you set the cache value directly, right? And then you can immediately just say that S1 is that value, right? So that went from 5 lines to 3 lines. Or you can do something like this. S2 is coins, right? S2 is coins. Okay, yeah, just that. This has to be, you have to do it this way because you have S1 no matter what, right? S1 either exists in your cache or it doesn't. So this is a cleaner way to go from 5 lines to 3 lines if you want it to do the cache it that way. Here's a better way, is to, okay, you have your value subproblems you computed. Right, this is my subproblem cache, and just make one recursive call step and then check whether that exists. But let's move on. I call this DP. Might be a bit misleading. I did this a while ago. This can actually, so this is, we're gonna do the iterative method of dynamic programming, right? So what I did here was a top-down approach. I started from my I started from the problem I wanted, and I branched off to small subproblems until I hit the base cases, which are gonna be the leaves of my recursive tree, and then propagate those values up. So in terms of runtime, this runtime is gonna be O of n squared, because I only have, like, I and j can only span from 1 to n. There are n values that both I and j can hold, and the combinations of that, different combination of having I and j is going to be n squared combinations. So that's why we have n squared here, because we you only see each subproblem, like you only need to compute each subproblem once. And once you compute it, you will reuse it, which meant that so all you have to worry about are the number of subproblems that exist, right? Because you compute, when you see the subproblem once, you compute it and you keep reusing it. So the runtime is going to be the number of subproblems that exist, which is going to be n squared. Okay, so that was the top-down approach. Here we're going to do a bottom-up approach in terms of iteration. Okay, so the bottom-up approach starts off from the very bottom of our recurrence, the very bottom of our recurrence tree. So I'm gonna start off with these leaves, and I'm gonna compute these values, leaf values first, so that whenever I move up, whenever I compute the next subproblem, I would always have the subproblems I need already computed, right? So it's kind of weird in the sense that, so let's do a visualization. Suppose I have, let's say, 6 values. I should probably use Excel. So let's say this is my I and j, and I go from 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's think about how we actually need to do this. Well, looking from my base cases, my base case consists of the fact that, okay, if I is greater than j, it's 0, right? So this entire side of the triangle is going to be all zeros because I don't really care about it, right? That I don't ever need these subproblems. Like, I don't ever have to worry about it. But now let's look at this case where we only have one element left, and it's that same element. So which is going to be this diagonal, right? For I to j, so 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. The next step is the two elements, which is going to be this diagonal, and so on. Right? Okay. What am I? So now you're trying to think about, okay, how are we iterating over these values? Let's make my. So I'm going to use a bigger. Okay, let's use this. So this is going to be bigger. So I have 0, 1, 2, 3, 0, 1, 2, 3, 4, 5. Okay, cool. Now I have okay, I can't draw today. But anyway, so just think about that. So we have 0, 1, 2. So these are my I indices, and these are my j indices. All right, let me just clean this up. Okay. So let's think about how we're using this. We have our base cases of the leaves. So these are our leaves. Am I missing one? Yes, I'm missing one. It's a struggle. All right. So these down here are going to be zeros. I don't really care about these values because that's defined in my base case, right? My base case was saying, like, if I is greater than j, it's return 0. So I don't care about these values here. So here are the values where I do care about are the I equals j, which is going to return a of I, right? So these values are the a of I. And then next step we're looking at the base case is we have two values, and we take the max of them, which are going to be that. Okay, so now let's look at the recursive case. So suppose that I am at S1, right? So let's say here, at this point, it's not covered by my base case. So if it's not covered by my base case, I have to go through this subproblems S1, 2, 3, and then choose left and choose right, right? So the three subproblems, S of 1. So S of 1 from here are going to be I plus 2, which is going to be this point. I plus 1 and j minus 1, which is I plus 1, j minus 1, this point. And then I and j minus 2. So j minus 2 is going to be this point, right? So it's going to be these three values that I need. So, and then here it's going to be the same thing, right? It's going to be this one, and this one. And if we go down these diagonals the same way we did for the two base cases, we have computed these subproblems already. So to compute these problems, all I have to do is look back on the problems that I have computed, which is going to be just these, right? So now let's code this up. Let's write some things. So the first thing I need, I'm going to call scores are going to be my cache. If you're not using Python, wondering what I'm doing, I'm just initialing my cache with all zeros. So see how I'm going from 0, 0, 1, 1, 2, 2, and then it's going to be 0, 1, 1, 2, 1, 3. So my very first loop, I'm looping on the gap. Like the gap between indices like I and j. And then for the second loop, I'm iterating over I. And it's going to be m minus the gap. Right? So if gap is 1, here, I stop at 4. If gap was 0, I stop at 5. So it's going to be m minus gap. And then finally, I have j is going to be equal to I plus the gap. Okay, so base cases. If I equals j, scores of ij is going to be equal to 0 a of I. I don't need the I is greater than j case because of the way I'm iterating. But I do need the case of this. I do need this because of the fact that I am using indices, and since I am using indices, I don't want to run out of room, right? Because like this second diagonal, if I were to actually do I plus 2, I run out of index. Like I'm going to be index out of bounds, which means I have to need this case. But I don't need the other case, right? So that's why I said it's optional, even though, so out of the 3 base cases, in top-down recursion, I needed these 2 to stop my, but in bottom recursion, I needed these 2 because this was automatically taken out by the way I'm iterating right now. But that's beside the point. Let's move on to the recursive. So I have S1 is going to be equal to scores of I plus 2. J. S2 is scores of I plus 1. J minus 1. J minus 2. Okay, so I have 3 subproblems. Now I have choose. So let's me take this code, right? So again, I make a choice. I'm going to choose between left and right. Scores of I. So the current value, ij position, is going to be the max of choose left and choose right. Right. So now when I finish both these loops, my final score is going to be here, right? So here is the answer, right? The subproblem from 0 index to n, or n minus 1 in this case. So this is the subproblem of the entire array, and that's where I want to find my final answer. And I know that it has to be computed last because I'm going in the diagonal. So score of 0 and n minus 1. Wait, no test. Okay, give me a sec. That's not good. Okay. Cache value of 0. Where is this? 108. Oh. I actually accidentally changed that earlier. Okay. So we're getting an index out of range here specifically because I have scores of 0 to n minus 1. Oh, yeah, we need. So that's for the this edge case is killing me. But the edge case is if n is 0. Okay, cool. So otherwise it's gonna work perfectly. Cool, nice. So this is gonna work. So what I did in the iteration here is that I drew out this diagram, right? And I saw that I realized that it went in this diagonal, and at a certain point I needed the 3 points over here. And if I compute it by diagonals, at each subproblem I can compute the values I need at constant time, right? So if each of these takes constant time, I'm gonna have n squared. So now my solution becomes n squared. Oops, freelance. Okay, right. So this is gonna be n squared, and I take n squared space. So this is time complexity and space complexity. So the cache, the top-down memoization. So this is called top-down memoization, where I use like a hash table or an array and I do it. So this is gonna be n. So I use the hash table here because you may not actually use n squared space, right? I use smaller. So you are using n squared space, but you're using less because I never computed these values. I only have I stop around here. So you use a bit less, but you sacrifice the time complexity for the space, right? And the time complexity is that you're sacrificing the extra constant factor of doing a recursive step and a cache check. Whereas in this, the iterative DP, the bottom-up approach, you're building your array, so you're sacrificing space for time. Because as you're building up your array, everything is done in constant time, right? Whereas in top-down, you do a check and you do a query on your subproblem cache. So that's sacrificing time for space. So those are two trade-offs between the memoization and the bottom-up iterative dynamic programming. So the next thing we want to think about is how can we actually optimize the space, right? Because if you think about it, after I compute this value, like this diagonal using this first diagonal, I never need this first diagonal again, right? And then, but I do need the second diagonal, right? So I have D1, D2, and D3. D3 needs D1, and D4 needs D2. So the one thing you can, so the main important point you get out of this is that once I use D1 for D3, I don't have to use it again, right? Which means that once I use D2 for D4, I don't have to use D2 again. Which means that all you really need is to keep two arrays like this, such that you can keep reusing the arrays and you rebuild your values up. So we're gonna build, we have two more implementations, which can be really quick. They're actually very similar in that there's just a tiny thing you can think about, but okay, scores 1. So the maximum array size that you need is just going to be that. Ooh, that's not a lot. All right, so I have 3 scores. And now I am going to do the same approach in the body of the iteration in the dynamic programming. But what I'm gonna now do is that I don't need J anymore, right? I don't need J anymore. So if gap 0, if I'm on the first diagonal, I'm gonna fill out S of 1 as A of 1. That's cool, right? If gap is 2, which is what this case is, I'm gonna fill out S of 2 with that. Okay. Now here's the cool part, is that I am, so at every iteration you're gonna build scores 3, right? Because I need to create the 2 arrays of my base cases first, and now with those base cases I can compute the values and use it. So let's think about this. So I wrote down the indices for a reason. and it was for this exact reason, was that if my subproblem was at index 1, what subproblems that I needed? So this is scores 3 of 1, needed scores 3 of 3, 2, and 1, right? I mean scores 1 of 3, 2, and 1. I needed, this is I plus 2, this is I plus 2 j minus 1, and then this is I and j minus 2. So the subproblem S1 is going to be S1 of my index plus 2, right? Subproblem 2 is going to be my index plus 1, and then subproblem 3 is going to be my index. And I do this. Okay. So the next thing we have to do is that after I finish the inner loop, I have to refresh my array. And if you're not familiar with Python, I'm gonna do a one-line assignment so that I don't have to keep temporary values. But okay, so the array that S1 was pointing at becomes S2 now, right? Because I am always using S1 to compute the values of S3. So once I compute this row, S3 now needs to be this one up here, and therefore S1 needs to move up. So to move up, I have that. Okay. If I were to make a new array for every time we're trying to build, this gives us back to n squared runtime, right? But I don't want to do that. But now I know that the scores 1 array is not used anymore, so I'm just gonna recycle. And finally, since I did a recycling, the last iteration of scores 3 becomes scores 2 after I finish this outer loop. So I return scores 2 of 0. Okay, so there's one more thing wrong with this, is the fact that I have these two down here. I only want to do a recycle if I only want to recycle my rotate my subproblems, so my subproblems arrays, only if the gap's greater than or equal to 2. Because otherwise, you're recycling your base case, and if you're rotating your base cases around at this third diagonal, you won't be using your base cases. You won't be using the first diagonal. So that's why we're gonna use we need to have this condition. Okay, hold on. Something is weird. Okay. There we go. Ugh. Scores 2 of I. Okay, so this is going to be I plus 1. Am I recycling? Where's J? Oh. No, I don't want this. Okay, I forgot one thing. Let's make that. That's still not working. Oh, okay. Yeah. I forgot I took out J earlier. Cool. So now we have the single array left. It's just edge cases. I don't know why I made this. Okay. But that will. Okay, cool. That'll work. Yeah, my edge cases that I added. But anyway, the idea was that I want to keep only 3 subproblem arrays cache and rotate them as I build my subproblems up. Now, the final one is that this is very, it's kind of complicated in terms of code. So we could clean this up a little bit if you would like and avoid some. So this will marginally increase our running time, not at a asymptotic level, but at a practical level, because you see how I'm iterating, I'm building up S1, S2, but I already initialized this array here. I could do this. Either I keep this as empty, right? And I just do an append. So I can do an append like this. Because I know I can only do this for score 1 and score 2 because I know that that had to be the last. These had to be the first 2 arrays that are built, so I could do it this way. The other one that's way a lot cleaner is just do this. Just build it up out top. Right, I can just build my array for I. This is I plus 1. I can build my array up out top here, which means that I do not need this if condition. Right. I don't need that condition. And the good thing about doing this rather than doing an append is that I don't need this condition either, because I can totally just avoid starting my gap off at 2. And now you get a n squared time complexity and a linear space complexity. Right? So the best time we can do is this. Okay. Right? So you see how we went from like the very naive list slicing tree recursion to a more memoized top-down dynamic programming to an iterative dynamic programming, and then once we've optimized the time, we've optimized the space complexity by reusing the same subproblem array and re-editing that, and so we get our final solution. So I hope this helps. I hope this helps you understanding kind of in a more practical level of dynamic programming, as well as how to like approach this problem if you were to see a similar one on a midterm. And I know it's long, and thanks for watching.